Welcome back, friends. So in the previous class we have seen how to find out the Fourier series coefficients if it is a square wave and if it is symmetric square wave. That means if it is a even symmetry or odd symmetry. If this kind of symmetry is there, I told you there are four kinds of waveforms. So for those four kinds of waves we have seen, suppose if there is a jump, everything is a positive. If there is a jump which is a positive, then everything is a positive. If a jump is a negative jump, then it is everything is negative. If there is no jump, only amplitude is there, then if it is a positive amplitude, we can say everything is plus minus like that. Now if it is having what we can say negative amplitude, then it is minus plus minus plus. So, and I told you how to find out the Fourier series coefficient. The formula is 2 into maximum value minus minimum value by n pi. So let's say based on this we can do one question. It is having so many sub questions. Let's say question number 9. Question number 9. Okay, so this is the waveform they have given, and the first question is find the Fourier series representation. Find Fourier series representation. First question. Find Fourier series representation. Okay. First, let's see how we can say it is again a symmetric square wave with a hidden symmetry. So it is having hidden symmetry. In that hidden, suppose if I change the DC value here, then it is going to have odd plus half wave. Odd plus half wave. And if you observe carefully, at 0 we are having a jump also, that is positive jump. Positive jump. So from this we can get the information. Let's say first, what is A0 value, that is DC value. Because it is a hidden symmetry, we are having the A0 value also. How we can calculate that? Area over one period. So for a period we have to calculate the area, that is A into 1. A into 1. Next, here there is no area. By total period, which is nothing but 2. Finally this is A by 2. A by 2, A0 value. Next, what is AN value? Which is 0. AN value is equal to 0. Why AN value is equal to 0? Because AN value is equal to 0 because it is having odd symmetry. Next, what is BN value? 2 into maximum value A minus minimum value 0 by n pi. That is 2A by n pi. The 2, it will take only odd values of n. Odd values of n only. That's only the thing. Now, next one more thing. What is the omega naught value here? Fundamental frequency, omega naught. This is 2 pi by t. That is 2. So 2 to get cancelled. Pi radians per second. Because time period for this is 2 seconds. Time period for this is 2 seconds. Okay. Now you can write x of t. Now you can write x of t. So what is that? First, A0 we are having A by 2. Now we are having a positive jump, so everything is a positive term. So what we can write? 2A by pi sine omega naught t. Omega naught value is equal to pi plus 2A by 3 pi sine 3 omega naught 3 pi t plus and so on, because omega naught value is equal to pi. So this is the expression for Fourier series. Clear? I am explaining it again. First, whenever a waveform is given, we have to observe what is the symmetry present in it. So it is having a hidden symmetry in that odd plus half wave symmetry, and we are having a positive jump. So positive jump means everything has to be plus 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 like that. We can calculate a0 value, that is a by 2, and an value 0, bn value 2 into maximum value minus minimum value by n pi. So from that it is 2a by n pi. Omega naught value is equal to pi. Like that we are going to get, this is the expression what we got. Clear? Take it first. Next we will see the second question. Draw the spectrum. Okay. Second question. Draw the spectrum for polar form of Fourier series. Polar form of Fourier series. So what is an value? An is equal to root of small an square plus bn square. So from this we can say an value is 0, bn value is there, so it is directly bn. So how much it is? 2a by n pi for odd values of n. For odd values of n. Then what is phi n? Minus tan inverse dn by an. So here an value is equal to 0, bn value is there. So it is nothing but tan inverse infinity, which is nothing but minus 90 degrees. Tan inverse infinity is equal to 90 degrees, so it is minus 90 degrees. Clear? This is what the phi n. Now we have to draw what is the spectrum. Otherwise, see, without calculating an phi n, we can say the same thing from here also. How? This can be written as a by 2 plus 2a by pi. Can you convert this into cos? Yes. Cos pi t minus pi by 2. Suppose if it is cos theta minus pi by 2, then it is going to be sin theta, like that. 2a by 3 pi cos pi t minus pi by 2. Pi t minus pi by 2. Sorry, 3 pi t minus pi by 2, like that. It will keep on going. So directly if you observe carefully, this is a0 value, this is a1, this is a3, and what is this value? Phi 1, this is phi 2, like that. So every value is nothing but minus 90 degrees. And what is a0 value? That is same as small a0, that is a by 2. Now if I draw the spectrum, let's see how it is going to look like. First, magnitude spectrum. Magnitude spectrum. An versus n omega naught. Zero. First frequency, which is pi. Next 3 pi. Next 5 pi, like that it will go, and so on. In the similar manner, we can go for phase. phi n, 0, pi, 3 pi, 5 pi, and so on. Okay, so I am just writing that expression what we have written, a by 2 plus 2a by pi sine pi t, 2a by 3 pi sine 3 pi t plus 2a by 5 pi sine 5 pi t plus and so on. Okay, so we can write in the terms of cos like that. So let's see how we can draw that. At 0 we are having a by 2 magnitude, phase 0. At pi we are having magnitude is 2a by pi, 2a by pi, which is greater than a by 2, 2a by pi. Next here we are having minus pi by 2. Phase is 90 degrees, which is minus pi by 2. Next we are having 2a by 3 pi, phase angle minus pi by 2. Next 2a by 5 pi magnitude. Next phase angle again minus pi by 2, and so on it will go, and so on it will go. So this is what is nothing but magnitude spectrum and phase spectrum. This is what phase spectrum. Phase spectrum. Clear? Take it. In the same ninth question, third question, sub question, third question. Let's say 9.3. 9.3. If the above signal is passed through a band pass filter, with a center frequency of 10 pi radians per second, 10 pi radians per second, and bandwidth of 4 pi radians per second, then obtain the output. So this signal is passed through a band pass filter with a center frequency like that. Then what is the output? Okay. If it is a band pass filter, this is how it look like. Characteristics. Its characteristics looks like this. Omega 0. Let's say h of omega. So what is the center frequency they said? with center frequency 10 pi radians per second, 10 pi, and bandwidth is equal to 4 pi radians, 4 pi radians. If bandwidth is 4 pi radians, then it is 2 pi radians, this is also 2 pi radians, then it is going to be 8 pi, and this is going to be 12 pi. Now we are having the signal. If the signal is passed through this band pass filter, if the signal is passed through band pass filter, then what is the output? So first try to understand what is the input we are having. Input. In the input we are having 0, first 0 frequency, next pi frequency, 3 pi, 5 pi, 7 pi, 9 pi, 11 pi, 13 pi, and so on. These kind of frequencies what we are having. If these frequencies are passed through band pass filter, what kind of frequencies comes out of the output, at the output? So first let's see, up to 7 pi, which is outside this. Next we are having 9 pi and 11 pi. Only these frequencies will flow or will pass through this band pass filter. So the output is we are having the frequencies which are 9 pi radians per second and 11 pi radians per second. 11 pi radians per second. So these are the frequencies what we are going to get out. Now let's say what is the output? With 9 pi frequency, 9 pi frequency means ninth harmonic, because omega naught value is equal to pi. So 9 pi frequency means ninth harmonic. What is that? 2a by 9 pi, 2a by 9 pi sine 9 pi t. This is the ninth harmonic component. 11 pi means 11th harmonic component, because omega is equal to pi, omega naught is equal to pi. 2a by 11 pi sine 11 pi t, 11 pi t. So this is the output what we are going to get. Clear? Take it. The power of 10th harmonic. How much? First of all, 10th harmonic does not exist, because it is having only odd harmonics. Even harmonics does not exist. So I can say 0 watts, because even harmonics does not exist. Does not exist. Does not exist. Next, 9.5. The power of 11th harmonic. Power of 11th harmonic. First of all, what is the 11th harmonic? Is it existing or not? Definitely it will exist. 11th harmonic is equal to 2a by 11 pi, 2a by 11 pi sine 11 pi t, sine 11 pi t. So this is what the 11th harmonic. Once we know the 11th harmonic, which is a sine wave, then we can calculate the power directly, because it is a periodic wave. RMS value square is nothing but the power. So what is the RMS value? Suppose if I take this is a Vm, then it is Vm by root 2 is nothing but the RMS value. For that we have to take the square. So what is the power of 11th harmonic? Which is 2a by 11 pi by root 2. This is the RMS value. We have to make square. We have to take the square of it. That's what the 11th harmonic. Suppose if I ask kth harmonic, kth harmonic, And remember, k is odd, that is odd. Here where k is odd, because even harmonics does not exist, so we have to take the k is a odd value. Then what is the power of kth harmonic? Power of kth harmonic. So for this wave, 2a by k pi, 2a by k pi, which is nothing but the 11th harmonic amplitude by root 2 RMS value whole square. In general, I can write power of kth harmonic is proportional to 1 by k square. Clear or not? So it is nothing but 1 by k square. If I ask question number, let's say 9.6, 9.6, ratio of power in fifth harmonic to power in seventh harmonic. Power in seventh harmonic. What it is? Power of fifth harmonic by power of seventh harmonic. That's what we have to find out. So just now we came to know power of kth harmonic, if they are odd, directly we can go over 1 by k square. So it is nothing but 1 by k, that is 7 square by 5 square, inversely proportional to the k. So it is nothing but 49 by 25. 49 by 25. So this is what we are going to get. Take them. This is already we know. No need to take this one. Question number 10. A 10 kilohertz, even symmetric square wave, even symmetric square wave even symmetric square wave passed through a band pass filter, with center frequency 30 kilohertz, with center frequency 30 kilohertz and 3 dB pass band, is 6 kilohertz, then the output of the filter is, then the output of the filter is options. Option A, a highly attenuated square wave at 10 kilohertz, Option B, nearly zero, Option C, nearly perfect cosine wave at 30 kilohertz, Option D, nearly perfect sine wave at 30 kilohertz. At 30 kilohertz. At 30 kilohertz. Okay. So see the question. A 10 kilohertz even symmetric square wave is passed through a band pass filter with a center frequency 30 kilohertz and 3 dB pass band. 3 dB pass band means bandwidth 6 kilohertz. Then the output of the filter is. Okay. First try to understand even symmetric square wave. Even symmetric square wave means, so it may be hidden symmetry or it may be having half wave symmetry, we don't know exactly. So definitely it is a even symmetry. So if it is a even symmetry, it is having inside definitely a half wave symmetry. So it is having odd cosine terms. So I am writing that because it is a even symmetry. Even symmetry. That means it is having only odd cosine terms. Odd cosine terms. Odd cosine terms. So if it is having odd cosine terms, let's see. First, what is the fundamental frequency? F naught. That is given as 10 kilohertz. 10 kilohertz. Then what kind of frequencies it is having odd cosine term means? F naught, which is 10 kilohertz, and 3F naught, which is equal to 30 kilohertz, and 5F naught, that is 50 kilohertz. These kind of frequencies what we are having. Now this wave is passed through a band pass filter. So what is a band pass filter? F. With the center frequency how much? 30 kilohertz. 30 kilohertz. And it is 6 kilohertz. 6 kilohertz. Then because it is a half, so it is a 27 kilohertz, and this is 33 kilohertz. This is what the band pass filter. For that, what is the input? That is frequencies 10 kilohertz, 30 kilohertz, 50 kilohertz. So at these frequencies we are having the cosine wave because it is a even symmetry. So we are having input as 10 kilohertz, 30 kilohertz, and it is 50 kilohertz, like that. 50 kilohertz and so on, and cosine terms. Now if you see 10 kilohertz is not going to pass through it. 10 kilohertz is not going to pass through it because it is outside the pass band. 50 kilohertz is also not going to pass. Only 30 kilohertz is going to pass, and that too it is a cosine wave. So the output is a 30 kilohertz cosine wave. 30 kilohertz cosine wave. That's what it is going to be output. So nearly perfect cosine wave at 30 kilohertz. So this is the option what we are going to get. Clear? Take it. See those questions. Question number 12. Here the circuit is like this. This is Vi of t. 5 ohm V of t, 2 Henry I of t. So no need of V of t now. And Vi of t is shown like this. Zero, 1, 2, 3 and so on. This is one. We have to shown is like this. Obtain third harmonic component of current. Obtain second and third harmonic component of current. Third, second harmonic component of current I of t. Okay. So they have given Vi of t and they want to calculate I of t, but not everything I of t. They want to calculate only second and third harmonic components. Okay. How we can solve this? First of all, you might remember in the LTI system, I told you for any LTI system, if sinusoid is given as an input, then we are going to get the sinusoid as the output with the same frequency, or we can say same period. This is what I told you. Now here also, if I want a second harmonic current, the voltage we have to consider is a second harmonic voltage. To get the third harmonic current, we require third harmonic voltage. That's what it is. So first, can you write what is Vi of t? Just now we have seen how to write Vi of t. Vi of t for this, a by 2, that is 1 by 2, plus 2a by, that means 2 by pi, sine pi t. Next, 2 by 3 pi, sine 3 pi t. A value is equal to 1 here. 2 by 5 pi, sine 5 pi t, sine 5 pi t, plus and so on. So this is what Vi of t if you write in the Fourier series. If you write in the Fourier series. Why we have written in the Fourier series? You may get doubt. Sir, why can't we apply directly the what we can say square wave and we can do the analysis? We don't have any analysis techniques for the square wave. We are having the DC analysis technique if input is DC. We are having the AC analysis if the input is sine wave or cosine wave. But we never have any analysis technique for the square wave. So that's why we have represented this square wave in terms of sine waves. Okay, that is nothing but the Fourier series. Now they want to obtain second harmonic current. So for that we require second harmonic voltage. Do we have the second harmonic voltage? No, because it is having only odd harmonics. This is the first harmonic, this is DC, and this is third harmonic, like that, and this is fifth harmonic. So for second harmonic current, it is going to be 0. Why? For second harmonic current, there must be second harmonic voltage, which is not present. So in that, the first one, second harmonic current is equal to 0. Second harmonic current is equal to 0. Now we require to find out third harmonic. Third harmonic. For that, what is the third harmonic voltage? Third harmonic voltage which is equal to 2 by 3 pi sine 3 pi t. 3 pi t. So we have to do the analysis with the AC by using phasors. So in the phasor form, let's call it as V3 phasor. V3 phasor means this is third harmonic phasor. 2 by 3 pi sine, and this can be represented as angle 0 degrees. Angle 0 degrees. Now if I represent this in the phasor form, this is a phasor voltage 2 by 3 pi at an angle 0 degrees, at an angle 0 degrees. Resistor is not going to change, 5 ohm. Inductor j omega L. J omega L, omega value is equal to 3 pi. So j omega 3 pi into 2, that is j 6 pi. J 6 pi. So this is what we got. Now we are going to get phasor current I3, that is third harmonic current. What is I3 now? I3 is equal to 2 by 3 pi at an angle 0 degrees by total impedance 5 plus j 6 pi. If you solve this complex number, you are going to get, the answer is 0.01 at an angle minus 75.14 degrees. This is what I3 phasor you got. Then if you represent this in the time domain, I3 of t, that is third harmonic component, is equal to 0.01 sine 3 pi t minus 75.14 degrees. So this is what the third harmonic current. Clear? Take it.